plot the same distance as a function of the subsystem size, where n is the size of that they are measuring. And you see that this distance decreases exponentially with the size of the T. So indeed, the more you measure, the more you measure, the closer it is to ensemble become. And the crosses here are for a case where the Hamiltonian theorem is integrable, so you don't expect. Integrable Hamiltonian is an Hamiltonian where you have a lot of conservation laws. And you see it is exactly like some constant because we don't expect to redesign if the Hamiltonian has infinite conservation laws. Yeah, and here they also plot the design time decay, tau k, meaning the time at which the difference between the projected ensemble and the k moment of the random ensemble is smaller than an epsilon number.
But here is the hardware, not the Scrooge ensemble.
This is the yes. This is the design. So this is another one. So this plot is taken from the first calculator, the next one.
Could this Scrooge ensemble be applied also to integral systems? Because in principle, if that density matrix has some conserved charge, we get the distribution of let's say it's conserves U1 charge or something. The distribution will also satisfy this, and would we then expect this to go to zero if we compare it not against this hard K design, the hard K movement, but the Scrooge shape?
I think that is also very important the basis in which you measure, right? Because if you have some conserved charge, suppose that we have conservation on the number of particles, then for sure there is a measurement basis where, for instance, you know that you have 10 particles, and if you measure the particle basis, and you get 7 particles, then you know that in the other part of the subsystem you will have 3 particles, right? So maybe there exists some basis which is non-revealing, but it's not so
obvious.
Yes. Because then it would be charged revealing.
Yeah.
But I think there are papers about matter equality where it's trying to understand if what happens in the terms of conservation laws. I think it tries to sort of generalize to ensembles. Like whenever you don't know what physics,
Generalize.
yes, exactly. Where they sum all the possible student ensemble that you get events in experimental. And the reason it comes to my mind is that at least there is one measurement, which is the measurement, the daily basis of the charge which is conserved, but can be really
Can I ask you a general question? So, say k equals 1 is ETH basically, and then you have a kind of a hierarchy of normalization.
Yes.
Is it possible also to kind of define a hierarchy of conservation laws for which like you thermalize in one sense but you don't in the other? So like some constraints that like doesn't allow ETH but maybe allows another kind of thermalization at higher K.
I I think it's
I think
proven
about
that
the-
it's like it's proven that
Yeah, or the other way around. Like,
yeah, I think in like to analyze the moment k, to analyze the moment k minus one
yeah.
is a given. But I think it's important the direction. The other way around shouldn't be.
But can you map like up to which K you thermalize to which kind of conservation laws you have in your system?
But more than conservation laws, like what do you think about
No, I'm thinking about the work by Pablo Sala where he has like two Hamiltonians that have conservation laws and break ergodicity, but then you sum them and you don't. It's PRX with Frank Polman. Yeah, the one by 2020, ergodicity breaking, right? The hyperspace fermentation rate. So there are two Hamiltonians that separately break ergodicity, but if you sum them, together they thermalize. So I don't know, I was wondering if there is a mapping between which kind of conservation laws you have and up to which K you can deeply thermalize.
But if you have conservation laws, I don't think you. I mean, you deeply analyze it on yes.
Yeah.
So I think the way to do it would be to take it analyze it with a sample. And I think Matteo Poli has some papers on this. I should look at that. And then check the distance. I mean, the problem is that it's Sara Murciano, because here, I mean, the way to do computations is, for instance, with these averages at the local fluid. Normally, you do something for some more specific state, like some global states that are other states, and then you can averages and compute these averages or fluctuations within. But in general, then if you want to do something more analytical, it's hard. So if you have these two Hamiltonians, so you can compute the distance numerically, but I'm not sure. But for sure the distance, like the reference point should be these, you say that they have some conservation laws, then you should consider some generalized problems. So this is for the, so in this sense, we can say that the system is deeply thermalizing to another sample, while so here in this plot, so this is the third moment, and here A contains only two sides, while here A contains 4 sides. So here is not super clear the difference, but here is much cleaner. And so in the green, the light green points are the ones where they measure in the X basis. You see that this distance basically is separated to the dot, while this dark green point, this dark green point, they are in the Z basis, and you can see that this distance is exponentially decreasing with system size. And so the system is deeply analyzing to a structure sample. Energy referred to this expectation value of Hamiltonian that I was mentioning before, and the dark lines are the expectation value of the Hamiltonian on XB, while these light lines, like the expectation value of the Hamiltonian on the post on the condition post measurement state, and they want to say that basically they yes. So the thing is here maybe there is an internalization to the generalized function, while here there is an internalization to the function. And that's I took down the calculations of global magnitude with a unit. So it was interesting to look at this story in the critical person. It was very hard to manage to compute the distance. And so then I decided to change the protocol in order to get something that was well and rather than